let's go for it.
Let's go.
Ignacio, do you want to introduce, or should I introduce, or?
I'm happy to introduce. I see that Fernando had on a slide, so very quickly, Fernando Ramos is an associate professor at Instituto Superior Técnico of the University of Lisbon, and he has a long history with the UK, as he did his PhD in the University of Cambridge and his master's in the not less famous Queen Mary University of London.
Ooh.
And his research interests span software-defined networking and network programmability, network security, and the application of AI ML to network control. But I'm not going to say much more since Fernando has a slide about himself.
Okay, thank you very much anyway for the introduction, and thank you for having me here today. And thank you also to all of you that joined. You know, still probably many of you recovering from CCOM submission. Okay, so today's talk is basically, I'll talk about internet architecture. So this is a sort of a slightly extended version of a talk I gave in November at HotNets. And it all started, you know, some years ago. And in fact, I was hoping John was here because it started like with a paper from John back from 2003. It was called Plutarch, maybe some of you know. And so the idea started there. But it's like I usually talk, so this is Plutarch on steroids, because we have all programmable networks and the you know, these things, the translators, they were not called translators in the original paper, I think. Interstitial functions, I think it was the name. But they are now, so at the time you couldn't, you know, you didn't have the hardware capabilities to build some of these translators, and you didn't have like the clean slate internet architectures that emerged later. And so everything started there. And so I'll talk a bit now about the use of translators to enable internet architecture evolution. Okay, so I won't talk much about myself. I had in here just a few pictures of some colleagues and friends. In fact, my advisors, John in Cambridge, and Dean White, also from the Department of Engineering. I think he's not in Cambridge now. And also the late Laurie Cuthbert from Queen Mary. So he was my great advisor at Queen Mary. Also enjoyed very much. And yeah, so and thank you, Ignacio. So as he said, so the IST is basically the School of Engineering of the University of Lisbon. I'm also a senior researcher at INESC-ID, which is a research lab that's associated with the university. Before all of this, I did like my licenciatura in Aveiro, which is my hometown. Okay, enough about me. So let's go. So first, I always, you know, some people ask, you know, if you're old enough, you'll know this movie, and this was basically the reason for the title. This amazing movie, really cool, with Bill Murray and Scarlett Johansson, Lost in Translation. So that was the inspiration for the title. Okay. So let's return to what brings me here today, internet architecture, and specifically, I will talk about the evolution of the internet. And since we're discussing the evolution of the internet, I think a biological analogy is appropriate here. So I'll introduce two terms that might be unfamiliar to some of you. So bear with me for a while. I'll try to make this clear towards the end. So the first concept is that of an epiphyte, okay? So here you can see orchids, which are epiphytes. Orchids, beautiful orchids growing on this pine tree, I think. And basically an epiphyte is a plant that's similar to a tenant, grows on the surface of another plant, which is, we can call it the host plant. Importantly, this is a non-parasitic type of organism. So the epiphytes, they do not like extract nutrients or water from their host, so they do no harm to the host. They only use the host for physical support. However, they are dependent on the host for that support, which means that if the host plant dies or fails, the epiphyte plant, the orchid in this case, will lose its support and probably may die or fail. So, but the important point here is that in this case, the underlay, which is the host, limits the overlay, which is the epiphyte. The second concept is that of mutualistic symbiosis. This is a bit more complicated. So this is an AI generated picture of a pine tree interconnected with an oak tree. So these are different species that form a mutualistic symbiosis relationship with a fungi network, interconnecting them. So this is interesting because this is a close relationship between different species where they both benefit. So they interact closely and they benefit each other. And this, in fact, has been like it has driven evolutionary innovation. It fostered diversity and new adaptation of species. And what's interesting here is that this is enabled by a fungal network that basically translates and facilitates nutrient and signal exchange between different species. Okay, but let's return to what brought me here, which is internet architecture. I don't need to say this. Of course, the outstanding success of the internet is unquestionable, right? And I would say it's like a testament to the quality of its architectural design. But we are also very much aware, everyone here in this Zoom room is very much aware of the limitations of the architecture, okay? So in fact, most of us, all of us maybe here, have dedicated our entire careers probably addressing some of these challenges. The most acknowledged one is the lack of built-in security, so leaving the internet vulnerable to different types of attacks like root hijacks, DOS, etc. And we've seen, from the initial uses of the internet that, the world has changed very much and has basically raised other fundamental questions about its foundational design, such as the fixed host centricity in a now mobile and content-driven world. That one of the limitations. Also, the difficulty of adapting and evolving, which I think is a key problem of the internet, and other limitations. So, for more than 20 years, we've been talking about these limitations of the architecture. And in the last, I would say, around 15 to 20 years, also, the research community has responded with very well thought out and innovative clean slate redesigns of the internet. So many architectures were proposed. Maybe some of you have proposed an architecture. It was very common, like, 15 to 20 years ago. We have, for example, Zion, which is that prioritizes security. We have networking named like ICN, NDN, elevating content as central. We have others embracing mobility, like mobility first is an example. And there are others like the expressive internet architecture, which really focuses on an architecture that's evolvable, okay, which is very interesting. So all of these, they were great designs, really well thought out, many interesting papers to read, but they all have a problem, or most of them have a problem, which is a lack of impact. I will argue later that there is one exception, and that exception is really important for this talk. But why the lack of impact in general? First, all these, they are clean slate architectures, and they all require a massive overhaul. So these clean slate designs, basically, they demand replacing or completely overhauling the internet infrastructure. So a lesson that we take from this problem is that any successful architecture, in my view, should be backwards compatible with the existing internet. That's like a lesson number one. Then each of these solutions addressed a specific issue or a selected few, right? And so they had this narrow focus. They were focusing on security, or they were focusing on content distribution, or something like that. And so a second lesson that we take from here is that the architecture should be, they should support evolution and adaptability. The problem number three, in my view, is that some of the designs that embrace evolvability, I just gave you the example of the expressive internet architecture, which is a very good example and a very interesting architecture. The problem is that it assumes that IP will be replaced by that architecture. But we know that IP is deeply entrenched and won't disappear overnight. So, any solution that must be built, in my view, on the assumption that IP will remain widely deployed for many years to come. And these are the three key problems. So what we've learned as a summary, that any new architecture should, in my view, first enable architectural evolution, ensure backward compatibility with the existing internet, and acknowledge the ubiquity of IP and account for its continued presence. So these are like three requirements of any new internet architecture. Fortunately, there is already a solution to these problems, and it was found in overlaying. So overlaying, if you know the history of Seattle, you'll understand this AI-generated picture. So this is, this is Seattle, like there is this new Seattle that's built on top of the old Seattle, part of the city, not entirely, which is a really excellent example of overlaying. Anyway, getting back to architecture. So we had a few years ago this paper Trotsky, which comes from a line of work that has been that started probably 15 years ago, and this is basically a framework for a backward compatible path to an extensible internet. So the idea is that it's an extensible and backwards compatible path to the internet. And the key idea is to introduce a new layer. So it's they call it in the paper layer 3.5, which is an overlay layer that runs on top of IP, or on top of an L3, to be more precise. So these new architectures, so for example, the clean slate architectures would be deployed on this L3.5 layer, leveraging logical pipes, as they call it, provided by L3. L3, which effectively is, at least for for deployment, we can imagine it to be IP. And basically it allows integration. And the important point is that it doesn't require an infrastructure overhaul. We have, we've been using tunnels for immense things, so this is relatively easy deployment. To show this with a picture, so this is the internet that we know and love, multiple, autonomous systems or domains, if you want, whatever you want to call them, and routers interconnecting hosts. The evolution through overlaying is basically, the idea is that you introduce these, what they call in the original paper, the Trotsky processors, which basically allow hosts to make, sort of tunnels, right? Across, from one host to the other host. So these hosts are hosts that speak the new architecture. And then you have in each domain towards the destination, you'll have these Trotsky processors that basically enable you to have these multiple L3.5 hops, okay? And that basically are the nodes of the new architecture. So the new architecture is overlaid on top of the L3 underlay. This is really a good example. It's a simple scheme, so it really simplifies the deployment because it's basically reusing the existing IP layer for L3 pipes without requiring this huge overhaul. So it enables architectural evolution, ensures backward compatibility with the existing internet, and also acknowledges the ubiquity of IP and its continued presence. The three requirements I mentioned so far. So what's the problem? The problem, and what I argue here, is that there is a missing requirement that I think is essential for driving the deployment of new architectures. And that's that the missing requirement is that the new architecture should enable other architectures to realize their full potential. Otherwise, there are no incentives to deploy them. And this, I will talk about this for the rest of the talk. Unfortunately, overlaying, like in the ORCIDs example, the epiphytes, the problem is that the underlay will limit the full benefits of the new architecture, okay? And this is in fact, in some cases, the underlay can potentially nullify the very reason for the new architecture if it's deployed on top of L3. And that's the key point. In addition, there is a related problem, in my view, which is it risks reinforcing the dominance of IP, which new architectures aim to improve upon, right? because the fact that you will just continue reusing the L3 pipes, okay, or the IP tunnels, it reinforces basically the dominance, right, of something that many say it's broken. There are other challenges, like the fact that a new layer introduces overhead via indirection, the fact that end hosts must operate under the same architecture, etc. In the paper, so you'll find my HotNets 2024 paper, you can see more examples. But the key point are these two, the first two. Okay, so let me use the Zion architecture as an example to explain this problem number one, that the underlay is limiting the full benefits of the new architecture. So just a brief overview of Zion, very quick. So Zion is basically a secure internet architecture that offers strong security, scalability, and control through these path-aware networking mechanisms and with trust domain isolation. So it's basically, we can call it like a secure by design multi-path, path-aware networking architecture. So for example, it has inherent protection, cryptographic protection against root hijacks. It is highly resilient against multiple forms of DOS attacks, etc. I will give more examples later, but this is the general idea. So imagine that we are going to deploy Zion on top of an L3 pipe that's IP. So it's our BGP/IP internet as we know it. So we know that the overlay has this protection against root hijacks, against DDoS, etc. The problem is that even though you have those protections on the top, as the L3 pipe used is vulnerable to these attacks, because we know that the BGP IP legacy internet we know is vulnerable, for example, to prefix hijacks and to several forms of DOS attacks. The Zion L3.5 running as an overlay would basically inherit this problem. So, and this is despite Zion having robust mechanisms that are incorporated to prevent the attacks. The fact that you're running on top of an infrastructure that's insecure basically inherits this problem, okay? And this is the key point. This is the key point, is that Zion deployed as L3.5 will inherit the problems of the IP network that's running below. Okay, and now I make a very strong claim. I argue that this would fundamentally undermine the rationale for deploying Zion as an overlay, okay? There is no incentive. And let me explain why with some evidence. So as I said, maybe I didn't say this yet. So, but Zion is basically the only clean slate architecture which has significant real world impact. So it's the exception that I mentioned in the beginning of my talk. We already have over 100 ASs registered in Zion, over 10 ISPs offering commercial Zion services. And so it's, you know, it's in production. So it's the only one that's really is having impact. But there is a very...
Oh, I'm not sure if you can see the chat, but Tim is asking whether this is a Zion talk. I guess you're using Zion as an example rather than as a Zion talk, right?
Oh, yeah. I'm only using Zion as an example for one reason. It's real. In the paper, we talk about Zion and NGN as examples, okay? But in here, I'm using Zion because I think there's factual evidence to show my main argument here, which is you cannot deploy, this wouldn't be deployed as an overlay. And this is the most important slide I have. Basically, production Zion operates on native, which is BGP-free infrastructure. It does not work as an overlay, okay? And more importantly still, Zion users have now required like certification to ensure, you know, from the ISPs that are offering Zion, to make sure that there's no interference between IP and Zion traffic and that there's no BGP involved in, you know, in the exchanges of traffic in the Zion network, okay? I think this is this is evidence that strongly indicates that the success of Zion would not have been possible as an L3.5 overlay.
So Ran has a question. I don't know if it's the same as the one in chat. Do you want to ask?
Yeah, I can ask it. So
Please.
what drove the adoption of Zion? Was that like government regulation or subsidy, or was that like these ISPs had financial reason to do that themselves without any government interference?
Okay, so this started basically with, so by the way, I'm not working with Zion. I don't have any papers on Zion or whatever. And I'm not involved in this. I enjoy the architecture.
Affiliate links first, at least. Yeah, just joking. Carry on.
But I think the reason was we had like in Switzerland, because this was like so Adrian Perrig is the person that is leading this effort, and you know, is a very well-known person in the security community and networking security community. And basically in Switzerland, the financial he was able to convince the financial institutions that this made sense. And so it started. So the first Zion network, like native Zion, so without IP, you know, nothing, interconnected these finance institutions in Switzerland. And with time, they moved. You know, there is a huge deployment in Switzerland, of course, but now they also have other points of presence in many other, you know, worldwide. You know, they're growing. They have like they claim they have in every continent, I think, even Africa, I think they had something. But anyway, you can see from the numbers. So you have many ISPs, etc. I don't know if this answers your question, Ran.
So I'm not sure. So I don't know if it's still like unregulated, or if now a new Swiss bank would have to join Zion as opposed to use the current.
Oh, no, I don't think so. So I don't think it's mandatory. No, I don't think. I'm not aware, at least.
So none of that came through the government. It was all
No,
organic.
no, I think this was merely, you know, we can call it commercial, you know, the need to, we can understand that, you know, the finance industry has some interest in having like something that's very secure, always available. I
Yeah,
guess.
the only question is, how do you get to the first bank, right? You come to the first bank, you say, okay, let's invest. You need to invest a lot of money in deploying Zion. You will have no partners currently, so you will not gain anything. But believe me, I will convince others, right? So it's a
I
hard
think the argument is you're getting a lot of security, and there's probably a secondary effect of regulation in the sense that the banking industry is highly regulated and probably reputational as well for Swiss banks because, well, Swiss banks.
But that's the thing, like you don't get security if you're the only one deploying that. You only get security if your partners also do.
Yeah. Well, I guess if
So
you can.
this is like the chicken and egg. Like, how do we start from scratch? We have to get significant adoption. How did they get there? I don't know.
I think they convinced the government to be compulsory adoption as a backup. I think that's what they told in the talk to ECL once. Anyway, irrelevant.
I think also Adrian gave a keynote in, was it 2023, the one in Paris, the Connext in Paris, where he talked a lot about all the stuff that he did for adoption.
Yeah, they were very, yeah. Yeah, you know, I discussed this with Adrian a bit. I know that in the beginning it was not, of course, it was not like a single institution. It already had like a network of institutions, right? And so, but I don't know the beginnings. So yeah, maybe you should invite Adrian for a talk here.
That's a good idea. I think Tim also has a couple of Cyan questions. I don't know if you want to take it. One is, well, so Cyan doesn't use IP. Yes, I guess it doesn't. So what does it use instead of IP? Do you want to?
Oh, okay. That's a good yeah, that's a good question. Zion is an inter-domain architecture. So intra-domain, still IP, still OSPF, whatever. Okay, so it maintains the intra AS, the AS intra AS infrastructure. This is an inter-domain architecture. So it's
You said it was BGP based, or is it not?
No. On the contrary, BGP free. Yeah, the goal is to replace BGP.
Oh God. Okay. Changing the wings in flight. Okay.
If Adrian was here, he would say, "Oh God, you're still using BGP." Okay. Anyway, for this, honestly, to me, it's a bit irrelevant what clean slate architecture I have on top, or what new architecture I have. To me, it's just a use case for the translation-based approach. Any other question? Okay, so I'll move. Okay, so since there is this disincentive in some way, in integrating or evolving the internet architecture via overlaying, we didn't came up, but we thought that translation was another decades-old solution for many networking problems, could be also a solution for evolution. Okay, okay. By the way, if you know Istanbul, you'll know that this is a bridge where you cross from Europe to Asia. Okay, and so the idea of evolution through translation is relatively simple. So you have direct translation between L3 architectures, right? And that's it. So the idea is to deploy the new architectures like in series with these bridging translators. Of course, the first challenge is you have to develop these effective and ideally efficient translation mechanisms. When I mean effective is that you should not be lost in translation, right? So in the sense that if you're translating from one architecture to the other and then to the other or whatever, you should not lose the semantics of the networks, and you should again gain the benefits that the new architecture brings. But there's I see now an opportunity with this in terms of deployment with and feasibility. We have these recent advances in fast networking software and programmable hardware, with programmable switches, SmartNICs, eBPF, and all that stuff. Offers an opportunity to build these efficient translation mechanisms running at line rates. Okay, and so the architectures, as I said, they are like integrated in series, as you can see in here, with translator basically converting the protocols and the architectural principles from one internet architecture to another directly at L3. So in here you see L3 IP, L3 Zion, L3 IP again. Okay, and this is kind of the same as the mutualistic symbiosis example I gave in the beginning. And the point here is that, we have architecture evolution because we stitch together different architectures. We're backwards compatible because we stitch the new architectures with IP. And then the most important thing is that the new architecture that it's deployed at L3, which means it does not inherit the limitations of any underlay connectivity layer, okay? And in my view, it also incentivizes, if we can build effective translators, we can get incentives for deployment of these new architectures, because in these new domains, the users retain the full benefits of the architecture. And that's the key point. Okay, so we have, one of the key points here is to build effective translators. So we have an initial prototype of IP to Zion and Zion to IP. We are also working on a prototype of IP to NDN and NDN to IP. So the first one, the IP to Zion, is already running, and it was running using programmable switches, so Intel Sofinos. And we were able to send traffic across from one IP host to another IP host, crossing a Zion network, in this case, the Zion Lab network. We are now in the process of evaluating this also in a native Zion deployment. So we will interconnect natively here our research laboratory with the Zion infrastructure natively. So this means via like an L2 link, and so that we don't have IP anywhere for the next evaluation phase. Okay, in the last part of the talk, I would like to discuss a bit, if translation really helps, if it has some future, and what are the challenges ahead. So first of all, let's look now a bit deeper into the Zion use case, not very, very deep, but I just, I have in here, I've included like this table with many Zion capabilities. So I included in here 5. The first 2 that I have in here, they are related to some of the properties of Zion with respect to security. For example, namely protection against source and root hijacks, and protection against router forwarding table exhaustion, so DOS attacks against the routers, basically. And so that we can understand what we lose with overlay and what we may not lose with translation. So if we have an overlay-based deployment, even though this is similar to the example that I gave in the beginning, the fact that the BGP IP underlay is vulnerable to root hijacks, you don't get protection against these hijacks. Of course, one can say, we are deploying the PKI, we have some deployments of BGPsec, and these, while they are not fully deployed, we may have partial protection. But as we know, we need for BGPsec, at least we need full deployment to get the old benefits, as many research works have shown before. In a translation-based deployment, since L3, so the Zion L3 is not dependent of anything under it. In the Zion domains, and I should stress this, it's only, of course, in the Zion domains, the cryptographic authentication and path verification mechanisms will ensure protection against these sort of attacks, okay? If we think about the protection against router forwarding table exhaustion, I can explain by talking about the mechanisms that Zion has. So basically Zion doesn't, it relies on, it's sort of a source routing approach. So the idea is that state is carried in packets, okay? So this is what they call packet carried forwarding state. So the state is not maintained in per flow forwarding tables. For that reason, it has this inherent protection against attacks that target, like DOS attacks that target forwarding tables. On the contrary, if you're again running Zion on top of an L3 underlay that, like BGP IP, you are prone to these sort of attacks. There is another capability that I think is very important in Zion, which is Zion is a path-aware network architecture, which means that the end hosts are aware of the paths. They know they are able to. They have visibility of the paths they choose. They can choose the paths they use to reach the destination. Okay. And so there are these 3 things, these 3 capabilities that I include here. There's more, so this is a selected few that I think are important. One is the possibility of multipath communication using disjoint paths when they are available. The second is path control and truthful forwarding, which means that the end host can choose exactly the path it uses. So if, for example, it doesn't trust some ASs, so it doesn't choose those. And it's possible to verify cryptographically that the packets did not follow any other path, but the one that the end host has chosen. And third, end-to-end bandwidth reservations that are resilient to volumetric DOS attacks. So these are 3 capabilities that Zion offers. Again, in an overlay, we can imagine an overlay gateway, for example, generating multiple tunnels for multipath communication. That's possible with tunnels. Or use tunnels attempting to follow only trusted ASs, or specifying tunnels with additional mechanisms for bandwidth preservation. So these are techniques that one can imagine being, enabling, a deployment to achieve these goals. But the problem is that, again, the underlay doesn't give guarantees, because the underlay paths may not be disjoint, for example. The underlay network may route packets through untrusted ASs, etc., right? And so this is something that, again, a translator gateway will enable these capabilities, because the translator gateway will be able to act as an end host, as a Zion end host. So it is able to set up multiple paths to the destination, enforce geofencing via truthful mechanisms like one that's called Epic, and also enable end-to-end bandwidth reservations with another mechanism from Zion called Colibri. Okay. I should note, however, that in Zion, the idea is that you give, you empower the end hosts and enable them to make choices, choose the paths their packets follow, do multipath, etc. Okay. In this case, in a translation-based deployment, it's the translator that acts sort of an intermediary end hosts and makes decisions on behalf of all connected end hosts. One can imagine empowering also end hosts, to use these mechanisms as they wish. But for that, we would need some sort of mechanism between the end host and the translator. If we go back here, in fact, I may have. So if we are here, so in here, if we have, of course, in this, the important thing is that we only get the Zion benefits in the Zion domains. And it's the translators that basically will decide what sort of Zion capabilities that are being used on behalf of the many clients that you may have in the previous network, in this case, in the example, the IP host net, the IP network. Okay, after this additional detail on the Zion use case, let me now go over some of the limitations and challenges. So one of the key challenges that we are trying to come up, with some ideas here is that it's achieving seamless end-to-end deployments. So as I said before, if we have an attacker, if we have two IP hosts communicating using a Zion network, there is a part of the path that we may consider secure, right? That is invulnerable to some of these attacks that I mentioned. But of course, the IP domains, they remain, of course, vulnerable. There was no change there, okay? And so one problem that we have is how do we how do we guarantee that more and more traffic, or that my traffic traverses these secure domains like the Zion domains? Okay, so of course a simple possibility would be to have a tunnel, okay, from the host to the translator, and that way you will reach to reach the Zion network. This is something that we are considering. So this is kind of a mix, a hybrid between using tunnels and using translation. Of course, you don't have, you are still vulnerable to several of these attacks anyway, even though you have tunnels on top, although you could have secure tunnels for some attacks, but not all. Something like this. This is just the example of a tunnel. Another possibility would be, and sorry, I'm very Zion focused because it's the examples that exist from an architecture that's deployed. But in Zion, they also thought about the possibility of integrating more and more of the IP traffic traversing their Zion network. And so they came up with this SBAS approach, which I think it's interesting not only for Zion, but for any architecture. If you want, and the idea is that you can allow customers of Zion that are not part of the Zion network, or they call it the federated network or secure network. So if you have like a server that is connected to this SBAS, okay, this SBAS is it means secure backbone AS. And so basically the idea is that you have a server that's in IP world and connects, for example, using an L2 link or a VPN or something, with some security. And you basically announce your prefixes using BGP, but then the BGP traffic traverses this SBAS, which is the secure network. You can see this as the Zion network. And towards the end, to the clients, this SBAS is seen as a single autonomous system. So it's kind of, you are able to attract traffic to the secure underlay, as they call it, because the SBAS is seen as a single AS. So you have less ASs in the root. That's the key idea. This is just showing like this as a potential approach to bring traffic to your new architecture, to incentivize, for partial deployments. The second limitation, the second challenge is, of course, the development of effective and efficient translator, as I said before, and this is our main focus in our project currently. And so we're just building multiple translators and multiple versions of different translators between different internet architectures. So we're looking at IP to Zion, as I said, IP to NDN, and we're also considering IP to Zaya, so the expressible internet architecture in the future. Okay, to close, a quick discussion. So first of all, when we talk about new architectures, we have to talk about incentives for deployment. I think a very important and positive point of translation is that you may retain the full benefits of the new architecture as you're running the new architecture as an L3 architecture, which may encourage adoption because you have the full benefits of the architecture. However, it's difficult to ensure the end-to-end benefits, and this poses sort of a disincentive. One argument that sometimes is made as problematic when you're considering translators, I remember from the original Trotsky paper that proposed the overlay-based approach, that they mention this idea of using translators. And one of the problems is that if you have n architectures, you will have, in theory, n squared translators, which is correct. However, I would argue that, first of all, the number of architectures is expected to remain small, as we see with the clean slate designs that we have so far. We have less than 10. And so n should probably be small. More importantly, initially at least, the translators will focus on bridging the new architectures to IP, to the legacy internet, right? And so most translators will be new architecture to the old IP, which means that initially at least you'll have a linear growth with the number of architectures. Finally, if you want to translate directly between new architectures, like new architecture A, translating to new architecture B, you can just compose indirectly via IP. So you have those translators from the new to the old, and you'll just compose them together. And this may reduce complexity or cost. There's more details in the paper for more problems and discussion points. Okay, to end, because it's almost 5 and we need to go to the pub, right? First of all, overlaying like epiphytes, they rely on an underlay, which limits the overlay's potential. And by offering only partial benefits, this may deter deployment for some architectures. And I gave the example of Zion, which seems very clear in that respect. Translation, on the other hand, like mutualistic symbiosis, allows both these new and old architectures to retain their full potential. The challenges arise more in achieving these seamless end-to-end deployments. I end with a possible path to adoption. Maybe combining both is not, like the overlaying and translation may be interesting. So for example, we could consider using overlaying on IP for quick deployment because it's just faster to use just overlays. And this will enable end-to-end connectivity, although we may only get partial benefits. And gradually we would introduce translators to expand the reach of full benefits. And maybe this could be like sort of an incentive-driven growth, could generate an incentive-driven growth where, with translators unlocking these full benefits, hopefully they would create a snowball effect to drive further adoption. And with that, I conclude, and I'm open to more questions. Thank you very much.
Thanks, Fernando.
Oh, thank you.
Thank you.
Questions?
Yeah, I have one. So what did the Zion folks out of that? I'm sure you spoke with them, so what was their reaction?
No, it's in fact I've been I've had many conversations with Adrian Perrig specifically and other folks in the Zion team, and they were very so Adrian in particular is incentivizing very much this work, right? Because he thinks that overlays that do not work for Zion, right? And that slide that I said is the most important one. Basically results from a conversation with Adrian, because basically he told me, how they are deploying Zion. And I thought, okay, now I understand that, overlay wouldn't work in your case. And so I think it's a huge, it's really a clear evidence that at least for Zion, overlay wouldn't work. I'm not sure if translation is alone. It may not be, it's difficult. I think the deployment of translators is more complicated because it's like having tunnels is much easier. But on the other hand, it's like, Zion effectively has translators between IP and Zion. So they are doing this already. They don't call them translators, and they do this all in software, so they don't run this in programmable switches, etc. But so they're interested in this, right? And in fact, I will give a talk in next week on this, on the Zion. They have this
in this forum again.
Yeah. It's this one again. In fact, I will give like the same talk 3 times in 4 days or 5. This is the first, so I'm not yet tired.
Can I ask a question? Fernando, great talk. I'm quite a bit of a philosophical question. I'm not sure if it's philosophical, but me and many people, I think, are one thing that I feel ashamed is how slow the internet evolves, right? I mean, we take like 30 years to add some bits to the IP address header, and it seems that other areas of technology don't have this problem. I mean, for example, look at mobile networks. They have one new technology every 10 years. Everybody changes phones. Everybody upgrades their equipment. They're not backward compatible. They actually switch off the previous one. And so I'm not sure why are we so ossified? Why is TCP so ossified? Is it something intrinsic to IP, or is it something the way we organize ourselves to build it and to regulate it?
That's a good question. Sort of techno-philosophical.
Yeah. I mean, because current solutions, I think, we have to get to the root of the problem, and I'm not sure we got to the root of the problem.
I think the key point is that IP is like in the center of everything, right? It's like it's the narrow ways, right? And everything talks IP. So all of these other technologies that you're talking, as we know, it's like either above or below. We have communication because we have the narrow ways communication across everything.
Yeah.
So every new development and those that you mentioned, they are all using IP, right?
They are now, but
they are now.
Yeah.
Sure.
2G, first 2G, 3G, they didn't really have. I mean, they seem to have they paced themselves in a different way to force themselves to upgrade every cycle, and we just don't have that. I mean, Wi-Fi is another thing, right? There's a Wi-Fi every 5 years.
Yeah. But it's like if you want to have global connectivity, you need an L3 protocol, at least
Right.
with the current way we see the internet architecture, and that's L3. And L3 is like L3 IP, and that's entrenched everywhere, right?
Yeah.
So everywhere. It's in the software stacks. It's in every single router and every single piece of equipment that allows you to interconnect globally. And so that's the problem. That's why, in my view, thinking about new L3 architectures, just leave IP as it is and just start coupling more, right? And either via overlaying, honestly, or translation. But I think overlaying has the incentives in fact, to me, the incentives are a bit, they're not the right incentives with overlay because it's just entrenching IP further.
Yeah.
So I have another question. I probably missed it in the talk, but you had the slide where both the source and destination were not part of the Zion network. Then you had 2 translators in the middle.
Yeah.
But then if the end-to-end connection, if both the source and destination are outside, what are the benefits that you actually get for security? So why would you want to translate a part of the path?
You get benefits of security if the packets are, for the part of the path that crosses the Zion network, right?
But so the source and destination, what would you do differently if you knew 80% of the path is secure?
Yeah. Okay. the thing, okay. The question is, yeah, what you're asking is, okay, if I only get, what is that of having 80% of a secure path, right? Yeah, I understand your point. You know, to me, it's like if you it's like if you're communicating and if your traffic process, you know, even if you know that there are a few parts of the path that are insecure or slightly insecure, and there's others that's secure, if I can go at least part of it, like in a highway, like when you're driving, if I can go in a highway for a while, it's better than nothing, right? I see it similarly. It's even if it's not everything, at least it probably we will surely diminish the probability of an attack, I guess.
Yeah, I would think of security as like it's only as strong as the weakest link, and if your weakest link is not secure,
I'm not sure. It may be in certain scenarios, right? I'm pretty sure that there are security properties. But on the other hand, it's like if you have 10 hops and if you have 8 hops in the middle that are secure, I'm pretty sure that it's like, you know, you will just probabilistically, you'll have less probabilities of an attack, I guess. That's a, yeah, but I don't know how to answer. I'm just, this is my view, but it's like
just
the weakest link thing is also, but I would say it's not like bandwidth, right? Bandwidth is different.
I have one question from my side. So you had at some point you mentioned efficient translation. Is efficiency an issue? Is there a performance overhead?
Well, it may be. So, for example, currently, as I said, you know, there are already, you know, Zion to IP translators. They do this in software, right? And we can say, you know, software is not really efficient. You know, doing things in a CPU is not an efficient way of processing packets, right? And you may imagine, you know, if we do this like in a programmable switch ASIC, it will be more efficient, you know, energy and energy-wise, for example, or packet processing time-wise. And so that's what I mean by efficient. Because we can do, you know, you can definitely build any translator if you have the full power of, you know, a CPU. The problem is that it may be very, very slow. For example, in Zion, you have lots of crypto, right, to be done, and that's a big challenge. In fact, for Zion, for the core network, if you really want all those properties, and if you want, you know, modern speeds, you will need specialized hardware, in my view, to do the crypto.
Right.
So it's not like a Tofino switch that will help you with this. You know, we're doing some crypto with the Tofino, but it's you know, we like to do this because it's fun as researchers, but it will never happen. It's like in practice. But there are papers, you know, to be written there.
So kind of following on from that, right? So the efficiency is one issue, but then if you allow this translation, overlay, underlay, and everything, there will be different architectures that one may be really good for security, one may be really good for performance or whatever. Will you end up with like 1,000 different architectures and 1,000 square different translators, overlays, underlays, and then all the inefficiencies that'll end up with that? Will you ever get to a stage where you'll only have one, and maybe that one is actually going to be IP, and then you're back to square zero?
No, it's like the way I see it, I don't think we'll have 1,000. I think we'll have like 3 or 4. Maybe one that's more secure, maybe another one that's, you know, like I see that, you know, the ones that are more, maybe because it's the reality today, the 2 architectures that are more, that have been progressed more is like Zion clearly and NDN, right? Because there's been a lot of effort in NDN and other ICN sort of architectures. But those are the 2 that I know. There's nothing else, right? And we started doing this, like the future internet architecture projects, they started 20 years ago. In 20 years, they came up, okay, there were like 10 important papers and 2 architectures that are, one in production, okay, fair enough. The other one, just lots of research prototypes.
RFCs.
Yes, so, yeah. But you know, maybe in the future I will see, you know, we'll see some of these, and maybe then there is one that because, for example, Zion is really not fully competing with IP, because as I said, intra AS is still IP. It's the same, so it doesn't change. It's whatever it is. It's an interdomain routing architecture. It's just the problem. Zion sees that the problem is BGP, and I tend to agree with that. You know, BGP has lots of problems, and Zion solves a few of them.
All right. Any final questions? We are almost on the hour. So a couple of links that Ignacio's put in.
Oh, okay.
That's the link to Adrian's talk from Connext that I put in.
Oh, nice. So let me maybe I will stop sharing to check those links.
By the way, Miguel, my answer to this 4G, 5G thing is we don't actually, why do we need IPv6, right? So, you know, you can't convince someone to say we need IPv6. Whereas what you have is like, oh, you get a new phone with 10 times more bandwidth and then, you know, 50 millisecond latency. Do I need it? I don't know, but it's a new phone. It's shiny, cool. I'm gonna get that. We need to have sold IPv6 with faster, better, whatever. Yeah, you're saying something. You're on mute.
No, so that's a good point. I mean, yeah, IPv6 did not offer anything new really to the user.
Yeah, it offers.
But there are lots of architectures who do, right? And lots and lots of ideas who do bring us new stuff, and they don't get adopted.
Yeah.
Multicast, for example, clearly multicast could really enable things. It's not deployed. Yeah, but you take your point. Yeah, that is true.
So maybe I'll ask another question about the adoption part. I think, like you said, maybe if we can get some adoption, then like to get the ball rolling, this will catch on later. I think like Miguel has something similar, but why weren't we successful in things like, I don't know, IPsec, DNSSEC, and we will here, right? We have some things that we're trying to push for decades, and you know, the adoption rate go up, but very slowly, and it's unclear if we will ever get these widely deployed.
We didn't have Fernando's architecture to have the translation.
No, I really hope it will catch on. I'm just like wondering if
we had it.
What's
it was the Plutarch paper is from 2003.
Yeah.
Yeah. Cool. Well, a few more
the future will tell.
at least. Sorry, Ignacio.
I was just saying that the future will tell if indeed the main issue is backwards compatibility. Having translators that eliminate the need for backwards compatibility could actually result in adoption, even if it's scattered and niche.
Mm-hmm.
Are you, Fernando, prepared to take a bet on the number of future deployments in the future?
Okay, like in 5 years, I'll talk about the production translators we have out there.
Right. We will expect you at Cosner's to pay some rounds or to take some rounds.
Yes. Now I have an incentive.
Cool. I think that's a great note to end on. Thanks, Fernando.
Thanks a lot. Really interesting.
Good to see you. Good to see you.
See you. Bye-bye.
Fernando, bye everybody.
Thanks, everyone.
Have a nice weekend.
You too.
Bye-bye.
Bye.
Nice weekend.
Bye.